Hello. So, as previously stated, I am Chris Myers. I worked as an environmental geologist at Newark, Delaware. I went to school for geology at the University of Delaware, but I've been collecting rocks my whole life. So, the whole point of today is we're going to chat about the geologic history of Allegany State Park. And by doing so, we're also going to learn some basic principles of geology that will kind of help us understand the formation of the park as a whole. So, what exactly is geology? Well, geology is the history, processes, and composition of Earth. So geologists, what do? We study that. So we study mountains, we study glaciers, we study rocks and minerals and fossils. We get to break rocks open with hammers, which are pretty cool. And it's just a fun time. So one of the other things we can study is other planets and oceans and everything in between. So got to start off on where we are in the world. So I want to talk about, for those of you who have not been, Allegany State Park is located in the western part of New York, right at the tip of this yellow point. It's a beautiful park. It's pretty large. It consists of nice hills with streams that are kind of dividing the hills, beautiful valleys. It's just a beautiful area. There's some trees there. And if you were to walk around in the park and you were to look in their streams, you would find a rock called shale. In that shale, if you were to look really closely, you would find some fossils. And if you look at the fossils, you'll notice these fossils are little like ocean creatures. And you're like, okay, so ocean creatures in a rock. And if you were going to stand on top of some of these mountains, you would find a rock called conglomerate, which formed at a beach. And so we're like, okay, we're at this park in the middle of New York, and there's rocks from an ocean. So how did they get here? So that's what we're going to kind of figure out today. So stepping back, we got to figure out the scale of geology, kind of get an idea of the scale of geology. And part of that is the Earth is really big. So as I showed before, Allegany is a really tiny point here, but the Earth is absolutely giant. So when we're thinking about all of these geologic processes today, remember that they're happening on a huge scale. And speaking of scale, geologists use something called the geologic time scale. And that is basically geologic processes happen really, really slowly, millions of years. So for reference, the Great Pyramids of Egypt were built 4,000 years ago. But the dinosaurs died out 66 million years ago, which is a really long time ago. And the Earth is actually 4.5 billion with a B years old. So all these numbers are great for just yelling numbers at you, but they're kind of hard to understand. So to help us do that, I have a little nifty demonstration. It's my geologic history of the Earth timescale rope of geologic science. So if you want to pan this way, and you see the rope at this end, that tip right down there is our present day. That's today, we're living and breathing. And if you want to start panning the other way, we're traveling back in time billions of years at a time until we get to the start of Earth way down there, 4.5 billion years ago. So this rope is 75 feet long, and at that scale, every inch, which is about the distance from the tip of your thumb to your knuckle, is 5 million years. So if we want to start back here, here is the formation of Earth. This is 4.5 billion years ago. This is when there is a disk of dust and gas orbiting of what would become the sun, and the Earth and all of the planets formed out of this disk, and the Earth formed into a solid sphere, well, mostly solid sphere. And soon after that, the oceans formed. So now you have this thing of this big sphere covered in oceans. And for about 1 billion years, nothing happened. So let's fast forward. Now we are at 3.5 billion years ago. Something cool happened at this time. So it's been 1 billion years since the start of Earth. And now in those oceans, some life forms starts appear. Now these life forms are just little single-celled organisms like bacteria and algae mats. And in my opinion, they're kind of boring, but they're cool because it's the first life on Earth. And they're swimming around the ocean, eating up sunlight and pooping out gas. And they pretty much do that for the next few billion years, nothing much changing. So again, let's fast forward in time a few billion years, many billion years. after that long walk through time, we are now at 541 million years ago. So this time something really cool happened. So all of those life forms that were swimming in the ocean, not doing much, around this time, they all started to evolve really quickly. And at this point, something called the Cambrian explosion happened. And all of a sudden you get thousands of different types of organisms swimming in the ocean, like corals and undersea plants and animals with fins and gills and teeth and eyeballs all appear at this time. So this is where things get really interesting. So that happens, and oh, I forgot to mention, one of my favorite animals appeared in this time, something called the trilobite. This little guy scuttled around the ocean floor for a few million years. Unfortunately, he was covered by some rock and passed away, but now I get to preserve him and look at him every day. So, going to fast forward a few more million years from 541 million to 240 million years ago. The start of this colored rope, or this colored tape. Now, this is when the dinosaurs first appeared. They roamed the earth, they walked around, they ate and drank and made other little baby dinosaurs and pooped and did dinosaur things. Now, I am not lucky enough to own a dinosaur bone, but I do have this other fossil from a dinosaur. Now, this is called a coprolite. It is from a dinosaur, and coprolite is basically the scientific term for dinosaur poop. So this is fossilized dinosaur poop, and it may have come from a dinosaur just like this. So, little cool rock. You can buy these pretty cheaply. They're fun to have. So now, dinosaurs did their thing for a few million years, the whole length of this colored black and white section of rope, until we get to 66 million years ago. At this time, something really bad happened for the dinosaurs. A giant asteroid was flying around the solar system and decided to cross paths with Earth's orbit and actually slammed into Earth in what is now Mexico. And this created a huge explosion and tidal wave and firestorm, and soon many organisms, including almost all of the dinosaurs, died out. I say almost all dinosaurs because there is one type of dinosaur called the avian dinosaur, and this dinosaur actually did survive this event and continued to evolve into what today we know as birds. You might be hearing the birds around me right now, and those are actually living dinosaurs. So, as we fast forward in time a few more million years, we get to this blue line right here. Kind of hard to make out, but this is 2.5 million years ago. And this is when the Earth cooled down a lot. If you guys all heard of ice ages, this is when the ice ages start. The Earth would go through periods of cool and warm and cool and warm. And every time it got cool, giant glaciers would come down and cover a lot of Earth. And then as it warmed up, the glaciers would melt and retreat back to the North and South Pole. And so that happened for the next 2.5 million years. And this final black line, you can barely make it out. The width of this black line represents 300,000 years. And this is how long humans have been on Earth. When Homo sapiens first came into existence in Africa. And written history, so like everything you read in a history textbook, wars and culture and everything else, that existed for only a few thousand years, which at this time scale would be the width of a sheet of paper. So as you can see, geologic processes have occurred over the whole 4.5 billion years, and they happen really slowly, and it's kind of interesting to figure out how they happen. So I'm going to take a quick break, and I will see you inside in about 30 seconds, depending on how fast I can run.
And Chris is, Maggie has so politely turned off the cell phone as he walks through the house so you don't see our whole setup downstairs. Chris will be rejoining us in a second in our kitchen and has a number of topics to go through regarding his, he's got some rocks, he's got some great demonstrations pertaining to geologic time and glaciers, and I think you'll find it very exciting. So he should be joining us in a second. I need to spotlight him. I think here he is.
Hello. So you can probably hear me now, and soon I'll be spotlighted so you can see me.
Let me see here. Hold on a second. It's not loading. Oh, I have to unspotlight myself. Hold on. Go ahead, Chris. Can you talk?
Yes, I can talk. Can you hear me?
Yeah, but it's not allowing me to spotlight you. Hmm.
Let's see if our resident command or control center can help me out.
You seem fine to me. I see you and hear you.
Oh, perfect. Okay, if everyone else is good, let's start learning about some more geology. Ooh, I need to, where's that? Oh, it might be from you. Oh, there we go. Okay, so now we got that straightened out. One of my favorite parts about geology, or I'd say the best part about geology, is the rocks. This is the foundation, the bedrock of geology. So want to learn about the types of rocks. There are three types of rocks. There's igneous, sedimentary, and metamorphic. So we want to start learning about this today. So I'm going to hold up two rocks. These are both igneous rocks. And what igneous means is basically these rocks were once deep underground, and underground it's really hot. These are miles underground and so hot that actually the rock was melted and flowing and it was a liquid. And eventually the liquid rose up to Earth's surface and erupted out onto the surface and cooled. So this is actually a lava flow. You can actually see the flow lines as the lava flowed across Earth's surface. And this is also an igneous rock. It looks much different. It's like bright white. And this formed when basically the liquid lava, or it was magma because it never erupted out of the Earth's surface, came up really close and actually cooled underground. And they look completely different, but they're very similar. So I am going to hop over here and slideshow, start from beginning. So here we have examples of igneous rocks. They form from volcanoes. They're super cool. And off to the side here, to the right, we see a description of a volcano where we have this chamber below, and that's filled with magma. And then when it erupts out of Earth's surface, we call it lava. So that's how these two igneous rocks form. Now, I want to start talking about the next type of rock. This is the important one for this lesson today. This is sedimentary rock. Now, sedimentary rock forms when you have big mountains or other big land features with rock on them, and the rock starts to erode and starts to, basically you have bits and small bits of other rock. And those bits of other rock can fall out into the ocean and settle out in layers. And when those layers get pressed down really, really hard by the weight of the more layers of bits of rock above them, they'll actually be converted from little bits of rock into actually solid chunks of rock made of bits of rock. So geologists, we separate the different types of sedimentary rock by the size of the bits of rock that make them up. So I'm going to switch back to my view. So one of the types of rock is called conglomerate. Now this specific conglomerate is called pudding stone. And you can actually see the bits of rock in it are pretty big. Like there's a little pebble there, there's some pebble there, there's some sand up here. So this rock is made from big bits of other rock. Now, if we move down the bits of rock size, move to rocks, bits of rock maybe the size of sand, like you find at a beach. And when that sand turns into a stone, we call it sandstone. And so this was actually an old ancient beach, and where a little bit of sand was laid down here, and then another layer of sand was put on top, and another one put on top. And when this was buried under thousands of feet of more rock, it compressed this and turned that loose sand into sandstone. And you can actually feel it. It feels gritty like sandpaper. Now, if we want to move down to the smallest size bits of rock, let's say the mountains eroded and they ground down the bits of rock into the size of like baking flour, so like very powdery. And now this baking powder sized flour of rock moved down to the ocean and settled down, and that is called silt. And when that settled down, you get a big layer of silt. And when that gets compacted, it turns into siltstone. And this variety of siltstone is called shale. So yeah, we have big bits of rock, medium bits of rock, and small bits of rock. But then the fourth type of sedimentary rock is actually not made from bits of rock at all. It's made from bits of organisms. So this is called limestone. It's made from calcium carbonate, otherwise known as chalk. And this is the same molecular compound that makes up seashells. So when animals are swimming in the ocean, they have little seashells made of chalk, and they die, and their seashells sink to the ocean floor, build up a layer of seashells, and then that gets compacted and turns into limestone. So that is the fourth type of sedimentary rock.
And the last type of rock, so we have igneous from volcanoes, sedimentary from bits of other rock, and then we have metamorphic. Now this rock is kind of confusing. So it's the trickiest one to understand. It's basically when you have one type of rock and you bury it deep underground, deeper than the sedimentary rock, but not deep enough to get hot enough to melt. This rock gets just super hot, just about where it's about to melt, and pressed really, really hard, and the rock actually changes. It's still the same material, but it gets stretched out, and the crystal shape, you get new minerals started forming, just weird stuff happens. And you can think about this as like a caterpillar. A caterpillar will, let me just do something real quick, switch to this, and here we go. Slideshow. So here we have metamorphic. So you have a caterpillar starting. Caterpillar makes a chrysalis around itself, and over a few days will turn it into a butterfly. Now, the animal's still the same, as the rock is still the same, but it's just changed the way it looks completely. So here you can see these crazy rock on the right with these crazy bends and folds in it. And so that's a metamorphic rock. Actually, next we are going to talk about the layers of Earth. So, the Earth is a giant sphere, as we know, and we actually live on the part of the Earth called the crust. And the crust is made of cool rock. It's solid, it's crusty. Any place you've ever been, you've walked on Earth's crust, and you've picked up a rock that is part of Earth's crust. And even the oceans are just big bodies of water that fill in depressions in the crust of Earth. And this is actually a pretty thin layer. I think at most it's 25 miles thick, which is very narrow. And this solid crust actually floats on the next layer called the mantle, this orange layer. And this mantle, you can kind of think of it as almost liquid. It's kind of a mix between liquid and solid. It's super hot, the rock is super dense, and the crust floats and moves around on top. And as we go further in, we get to something called the inner core and outer core. Now, this is basically a big ball of liquid and solid iron and nickel. And if you've ever seen a meteorite, picked up a meteorite, they're made of iron and nickel, and those are actually from the cores of old planets that never actually came to be. So, as I said, the Earth's crust is the part that floats on top of the sphere, and the crust is actually broken up into about 8 to 12 pieces. And these pieces, since they're floating, they kind of move around separately from each other. And a lot of these pieces have their own continent on them. So the North American tectonic plate, as we call them, contains the North American continent. And the South American tectonic plate contains this continent of South America. So yeah, these continents move around and smash into each other. So we take a little closer look, and now we're seeing that we have a cross section, and we can see these plates. And these plates do lots of weird things. They can sink underneath each other, they can slide next to each other, and they can slam directly into each other. And so this is actually a really important thing to know. When two tectonic plates slam into each other, at the place where they slam, they actually create a giant mountain range. And to see how that works, I have a little demonstration, a tasty demonstration, if you will. So we have my delicious Snicker bar tectonic plates of science. So imagine this is one tectonic plate and this is the other, and they're floating on the mantle, they're moving around on Earth's crust, and at one point they start moving towards each other. And as they move towards each other, they collide, and watch what happens right here as they collide. They start hitting into each other, and the rock starts to get squished and starts to mound up, and look at that, it's rising up above everything else. So now this is a mountain range. So yeah, the same thing happens with tectonic plates. They'll slam into each other, and where they join, they mound up really high and create a mountain range. And so keep that principle in mind, because we're going to come back to that. And also feel free to do this one at home. It's delicious and tasty and really fun. A little messy though, you get sticky fingers. So now that we know about the types of rocks and how plates move around, let's start learning about how all this comes together to form Allegheny State Park. So as I mentioned before, Allegany State Park is in western New York. The rocks that make up Allegany originally came from an ocean and from a beach. And the rocks at the top of the mountains came from the beach, and the rocks in the valleys came from the ocean. So how did this happen? So to help us kind of understand this, let's pretend that we are standing in Allegany State Park. We're in a meadow. It is a lovely sunny day, and except for we are 500 million years ago in this park. So let's transport back in time, and instead of standing in the meadow now, we are standing at the bottom of a deep ocean. So this is my representation of where we are standing. So we have, we'll be standing right down here at the bottom of this ocean. There'll be tons of, this is the water surface, we'll be deep down below. And we can just imagine this. So as we look around, we'll be able to see, lots of weird creatures swimming around us. So now this is, 500 million years ago, after all these weird animals appeared, so we have all these weird corals and strange animals that look like they're aliens swimming around us. And as we're out here, there's some silt and sand and dead animals that are kind of raining down on us very slowly, and this will continue to happen for a few million years. Same thing, now we're moving a little bit into the future, into the Ordovician time period. And again, not much is happening. Where we are standing, we're in a shallow sea. There's some weird like nautiloids swimming around us. Those giant fern things are crinoids. But as we're in this ocean, to our east, where about New Jersey is actually the edge of one of those tectonic plates. So we're kind of near the edge of one of these plates. And so the edge of the plate to our east in New Jersey is minding its own business, and then all of a sudden it starts to collide with the plate next to it. So at this collision zone to our east, mountains start forming, just like the Snickers bar. And where we are, we don't really notice it that much, but there's definitely mountains getting created to our east, and our sea level might be rising a bit. So then about 380 million years ago, let's fast forward in time, we're still in a shallow sea, and this time all of those shells and everything else around us, we have some trilobites swimming around, we have some more crinoids, we have some plankton and jellyfish, and as animals with these calcium carbonate shells die, their calcium carbonate shells start falling down and filling up. And so raining down on us, we start getting some, need to switch back to this view. So yeah, now we're back in the ocean and we are again under a shallow sea, and some shells start falling on us. And the shells kind of fill up the ground around us, and we get this layer of shells down here. Okay, so we're minding our own business and moving a little further into the future. The mountain range to our east is still colliding and getting bigger. And as it gets bigger, we actually start rising up. We're no longer in a shallow sea, we're in an even shallower sea. And around about the same kind of animals swimming around, but because we're closer to those big mountains now that are to our east, some of the bits of rock that are eroding away from those mountains are making it out to the sea. And so as we're sitting here, little bits of rock the size of flour, like baking flour, starts falling on us. And so now we represent that we have this little layer of like silt-sized rock particles from those mountains falling down. And it creates another layer. And so, okay, we're still minding our own business. And we're going to fast forward a few more million years. So these mountains are getting even bigger and even bigger and even bigger. And now, instead of being in a shallow sea or even really shallow sea, we're actually standing right on a beach. It's a lovely beach. It's made of the beach. If you're walking on the beach, there's lots of gravel and rounded stones. And if you want to see what something that might look like that today, here is an actual beach of, this is like what exactly we'd be seeing. We'd be standing on this beach, waves would be crashing, we'd have mountains to the side of us, and we get some pebbles in our feet. And it's again a lovely day, and as those mountains start to erode, those now sand and pebble and gravel sized particles start falling on us, or not falling on us, just building up around our feet. So to represent that, I have some gravel. So now we have a layer of gravel and sand falling on us. And so awesome. So yeah, we're at the beach and we have a layer of gravel and sand now. And as you see, we have this continuation of gravel with silt and then this shells below us. And eventually, about 300 million years ago, something really cool happens. That mountain range that is to our east starts actually colliding with what is now Africa. And the whole area that we're standing gets lifted up really high into the air. And we are now right next to a giant mountain range. We're no longer in an ocean, and all of that sea has disappeared. So, to give you an idea of what that looks like, here we have something called, if you ever heard of Pangaea, it's a supercontinent. It's basically about 300 million years ago, all of the continents collided. And if you look, you can see Africa and North America, and right where they collided in between is a giant mountain range. And when I say giant, this mountain range is the size of the Himalayas, so the biggest mountains in the world. And these are in Nepal and India, but right now the Appalachian Mountains, so those mountains to our east are actually the Appalachian Mountains. That's what formed the Appalachian Mountains. And you can imagine that we're sitting in this picture on the left in this kind of meadow, and we have these giant mountains to our east. And these mountains, even though they're still giant and growing, they're still eroding away. So material from the tops of these mountains is rolling down the hills and starting to bury us. And we actually get buried under thousands of feet of material from these mountains. So now we're standing on what was the beach, but we have thousands of feet of rock above us. And the pressure of all this rock starts pushing down on us and pushing down on us really hard. And so hard that, in fact, that if you go back to this diagram here, we're standing here, that the pressure is so heavy pushing down from all that rock above us that the sand and gravel from the beach turns into conglomerate of hard rock. And this shale, this silty, silt-sized particles and silt below us turns into shale. And all of these shells below that get compacted so much they turn it into limestone. So now you have conglomerate over silt, siltstone over limestone. And something I forgot to mention is during the time that all of this silt was getting deposited and we were in that ocean, all of those creatures that were swimming around us may have got buried with us too. And so, or buried in that sediment too. So now you have not only silt, but you have the remains of old animals. And so now we have this layer of conglomerate, shale, and clay, or and limestone. And over the millions of years, again, this Pangaea formed about 300 million years ago, and that's cool. And about 175 million years ago, Pangaea actually breaks up. Africa and the United States split up. The Atlantic Ocean forms between the two continents, and the world kind of basically gets into the position that we know today, where we have the Atlantic Ocean and North America and South America and Africa and Eurasia above that. And again, all of that rock that was above us that actually created all that pressure to turn this sediment into rock actually gets eroded away. Same with the Appalachian Mountains that were huge. They start to erode away and become the rolling hills and big mountain range of the Appalachian Mountains that we know. And now all of this material that was above us gets eroded and washed out to sea. So now we're back to standing on top of one of these, on top of this conglomerate layer. And you imagine we're at the park still, we're on top of this conglomerate, and now there's streams flowing down through this material and actually cutting valleys into this material. So at the tops of the mountains, you have this conglomerate, and the streams are cutting the valleys down into the shale, into the shale. And so some of the shale, as it gets cut down, you start seeing these fossils start appearing. And you can find these shale with cool oceanic fossils in the beds of the streams if you're walking through the park. So now we kind of have the system of the park set up. We have conglomerate at the top of the hills. The rest of the park in the valley is filled with the shale, with fossils. And we're still a few hundred million years, or about 100 million years ago. There's still one more big event that's going to happen to the park, or well, I should say almost happen to the park. So about, as I said, 2.5 million years ago, if you're remembering back to the rope experiment, I mentioned that there was something called the ice ages. The Earth cooled off and ice started to cover the Earth. So about 2.5 million years ago, something cool happened. Oh, it's always something cool that happens. But here is my super realistic ice sheet of science. So this is just slime, but it represents what a glacier looks like and how it moves. So let's move to where we are. So here we go. We have North America. And yeah, 2.5 million years ago, Earth got really cold and ice formed up here. Now the ice moves really slowly, but it starts to slowly spread. It spreads over Canada, and eventually it'll make its way, I'll give you a little hand, will make its way down to North America. And if we're standing in Allegheny State Park looking north, we see this giant sheet of ice making its way towards us. And this ice is 2.5 miles thick in places. It's absolutely giant. And so we see this giant wall of ice slowly creeping towards us. And we're thinking it's going to run us over, but it doesn't. It stops about 2 miles, just 2 miles north of where we're standing. It'll actually continue to go further south to our east and to our west, but stops just north of us. And so when this glacier's flowing across the world, it's actually picking up rocks and gravel. And so now you have this big sheet of ice with the rocks and gravel underneath of it. And those rocks and gravel then are scraped along the surface, and it acts like sandpaper. So as this glacier's flowing, it's literally sanding away the earth. And so all the mountains and hills north of the park actually were sanded away by that glacier. But because the glacier never reached the state park, it never was sanded away. So that's why in the park you have actually a little bigger and sharper hills and sharper valleys than just north of us, where everything is a little smoother, a little flatter. Now, this happened a few times. So the glacier would spread out and then melt away and spread out and melt away. And when that glacier was melting away, you'd have still some big mountains like you do in Canada and the Rockies, and small glaciers would form in the valleys of these. And so here we have a glacial valley, my super realistic glacial valley of science. And if you guys are familiar with, what are they? The Finger Lakes, you'll notice that those lakes are all parallel lines. They look like fingers. And so these actually formed from smaller glaciers as the big glacier was retreating. And so these formed by basically you have this ice in a valley, and it starts to flow downhill. And it kind of creates this U-shaped valley here, and the glacier just slowly makes its way towards the bottom. And as it does that, maybe you might have, it gets colder and some more snow falls on top of the glacier, and now it's flowing a little more. But then as the earth warms up, you might have a little bit of melting. So we'll represent melting by breaking away a part of the glacier up here. So now the glacier is getting a little smaller. It's still flowing forward, but it's melting, and it starts melting and getting thinner. And if it melts too much, it'll actually completely disappear and make its way all the way back to Canada. So this is kind of what happened in the park, where glaciers came really close, and then they started even though they were moving constantly forward, it got too warm about 20,000 years ago, and they retreated all the way back, leaving Allegheny the way it is. And so if you were to visit Allegheny today, we're treated by not having been run over by the glaciers, and you can walk around the streams and find shale and old Devonian age, 300 million year old fossils in the stream beds. And if you go to the tops of the mountains, you'll find some of that conglomerate from the beach that existed a long time ago. So that kind of just sums it all up. So I'll put it off to questions now. If anyone has any questions they would like to ask me about geology, the geology of Allegheny State Park, or earth sciences as a whole.
You can unmute yourself and ask a question. I don't think, and you can also raise one via the chat function. So if you have any questions, feel free to ask Chris.
Chris?
Yes.
Hi, Paula Thomas. Can you explain to me, if the glaciers are coming down towards us, how does it retreat? That would be going back up, right? I don't understand that theory.
Oh, perfect. So let's take a closer look at this. So we'll have the glacier here. It's flowing down. So the glacier is moving forward. It's always moving forward. And so we can see that. It will actually give this one a few seconds and let it keep on moving forward. So we're standing here and the glacier is moving towards us.
But it's moving down. It's not moving on a flat surface, You're
talking about how the ice sheets move like over the landscape.
You say it's flowing down.
Yeah, it's flowing downhill. So this is
Downhill, right?
yes,
Okay.
it's flowing downhill.
Yes.
And so actually, if it warms up, the end of the glacier will melt and break away. Now it's still moving downhill, but the end is actually melting away faster than it can move towards us. So even though it's still moving towards us, the end is just melting and disappearing right in front of our eyes and turning into water. If that helps explain it.
Yeah, what you meant by retreat? It retreats.
Yeah, so they use the
Okay.
retreat. And so actually it just means if you're looking at the size, what part of the world is covered by the ice, that looks like it's retreating. But on a smaller scale, if you're actually looking at how the ice is flowing, because the ice will actually flow, it'll flow forward, but the size will get smaller and eventually the tip of the glacier will make its way back.
Okay, I understood. Thank you.
Oh, no problem. Any other questions? Any in the chat? Okay. So, hello.
Is there any glaciers left?
There are. So there's actually two types of glaciers left. So that giant glacier, that what I said, that when it covered the whole world, when it did this thing and covered lots of the world, this actually still exists in Greenland right now, where it covers all of Greenland. Let's go to Greenland. Is covered, let's make this properly to scale. All of Greenland is covered by an ice sheet. And same thing with Antarctica. Antarctica is covered by a giant ice sheet. Now, it is melting, but it still exists. But you can see those. Also, if you want, you can go to areas like the Rocky Mountains, right on the Rocky Mountains and Canadian Rocky Mountains in Canada. You can actually go and see these valley glaciers. I've actually been there. You can actually walk on the glaciers there. Again, those are all melting. So I would say if you have time, go and visit them while you can. They're a wonderful sight to see. And there's a few other glaciers around the world. There's some in Europe in the high mountains. There's some in South America and some of the mountains down there. But those are basically just remnants of the last ice sheets. And yeah, I would highly recommend bugging your parents to go see a glacier someday.
Okay, thank you.
No problem. And if you want, you can make your own glacier at home. This is the fun slime to make. You use Elmer's glue, water, and borax. You mix it together, and you get this great slime that's fun to play with. It's clean, and you can pretend to have your own glacier.
Thank you.
No problem. So it looks like that is the end of the presentation, unless anyone has any other questions or wants to see any rocks. It's a short presentation today, but I'll say thanks everyone for joining, and I might pass it off to Lon to bring us home.
All right. Hey, Chris, thank you very much. You did a great job. What I'd like to do is encourage everybody. We have, again, thank you. Thank Maggie. We have a great program coming up after yours from Longwood Gardens here outside of Philadelphia. One of their operations managers is going to talk about the effects of fire on the environment, and more importantly, how they use fire to control noxious weeds, etc., during using prescribed burns. So that's coming up right after that. If you'd like to register for that, you can go to Allegheny Nature Pilgrimage. That's ALLEGANY, naturepilgrimage.com/virtual ANP. So again, Chris, great thing. The other thing too is all these are being recorded, and you can, we'll be posting those both to our YouTube channel, our Facebook page, as well as our website. So thank you very much. And if you have any questions, feel free to send an email. If you have questions about this program or anything regarding Allegheny Nature Pilgrimage, send an email to virtualanp@gmail.com. Thank you very much, and hope to see you in some of our programs throughout the day. Bye-bye.
Thank you.
Bye-bye.